First, I would like to thank you, the organizer, for inviting me to this e-meeting. It's been very interesting. I'm here today to tell you about a new way to do optimizations, and it's a method we have applied to molecular geometry optimization. And I'm talking about Kriging and gradient-enhanced Kriging. Before I start, I would like to recognize the contribution of Ignacio Fernandez-Galvan and Gerardo Raggi, Christian Ritterhoff, and Morgan Vacher. And the code that this has been implemented in is, of course, the open Molecast package. I have an outline here. So first, I'm going to discuss some of optimization fundamentals, how we do optimizations today, and what the limits are of that. And then I'm going to introduce the Kriging and the gradient-enhanced Kriging, some basics. I will not have time to dwell into all the details, but those of you who are interested, I suggest you go into the literature. Then we're going to use the gradient-enhanced Kriging to introduce something we called Restricted-Variance optimization procedure, which is a new way of doing restricted step optimizations. Also, the gradient-enhanced Kriging, it contains hyperparameters, and we're going to discuss how some of these parameters are computed in a way that doesn't involve an optimization of the hyperparameters. After that, I'm going to show you benchmark results on 3 different sets of test suites, and I'm going to round up with a summary and a conclusion. Before I proceed, I would like to mention that similar works have been done by the group of Denzel and Kessner, and towards the end, I'm going to compare my results with those. So conventional second-order molecular structure optimization, we tend to use a Taylor expansion, which we truncate, and we normally use a second-order truncated Taylor expansion to describe the potential energy surface on which we're trying to find a stationary point. We might write it in this way, or we might write it in a vector matrix formalism. That really doesn't matter. We also augment this approach with that we introduce a so-called quasi-Newton condition in which the difference of 2 gradients should be equal to the difference displacement times the Hessian. And we use this equation to come up with various Hessian updates method. Usually when we do optimizations, we compute the energy and we compute the gradient at some arbitrary points. But we usually use an approximate Hessian because it would be just too expensive to compute the second derivatives. And to accommodate for that the Hessian is approximate, we use Hessian update methods to make the Hessian comply with the quasi-Newton condition. So the BFGS method is one such method. There are further improvements to these approaches. It's what's called the rational function optimization, where we recast this Taylor expansion and introduce a denominator, which gives us a rational function optimization. We further introduce a step restriction, which means that we don't step too far on this surrogate model. We say that we trust it within a specific value. When we have this restricted step rational function optimization, we have a parameter alpha here, which we change in the case that the suggested displacement is too long. We increase the alpha factor here and get it down such that it complies with that the suggested displacement, delta Q, is less or equal to our trust radius. So let me just briefly summarize some of the properties of this type of optimization method and surrogate model. So the first, I have to say that this is not an exact interpolator. With that I mean is if we have a number of data points, the surrogate model is only going to represent exactly the two last data points. Any data point that was previous to that, the surrogate model will not be able to reproduce. Furthermore, as we increase the number of data points, our surrogate model will never converge to the true function. It's just going to be an harmonic potential. And because of that, of course, it cannot describe unharmonic features in general. Also, we know from empirical studies of these kind of methods that it depends critically on the Hessian update method which is used. Furthermore, because it's a second order Taylor expansion, it can only describe one stationary point. And one crucial thing, this model doesn't tell you or give you an estimate on how big an error you have in your estimated energies. And because of that, we have to guess that. Now, Kriging is a different way of doing it. I'm showing you the equation here for Kriging. So I'm just going to briefly tell you, we're using internal coordinates here, and we have a trend function. Essentially, Kriging is a way in which the energy or a surface is a linear combination of known data points with coefficients in front of them. We determine the coefficients such that this linear combination, on average, has a zero error. Doesn't mean that the errors are zero for a particular point, but on average, it's zero. And also we determine the coefficients such that the variance of this expression gets as small as possible. If you do that, you get the Kriging method. In this formula, we have some matrices and vectors. I will not dwell into these details. I suggest those that are interested to go into the literature and maybe spend an afternoon in trying to find out what's going on. In this process, though, minimizing the variance, you need to figure out how different points correlate with each other. And here is where, for instance, the Gaussians or the Matern functions show up. In our case, we're using a Matern function that is of 5/2 order, which is a Gaussian-like entity times a polynomial. And we have these d's here, which describe the distance between data points. In our case, we compute those as follows, where we have the internal coordinates. So we have an internal coordinate, a data point at I and another data point j. We compute the distance between these two data points as this square root of this sum of squares, where k here indicates an individual element of the coordinate q, and q could be Cartesian coordinates, internal coordinates, etc. Also, you divide it with a characteristic length. The characteristic length is one of the hyperparameters of the Kriging method, and that is something you can optimize in order to get the best possible method. In our case, we're using internal coordinates, which means that the surrogate model that we use is translational and rotational invariant. If you used Cartesian coordinates, on the other hand, you will get the surrogate model that would not have those properties. As you proceed, though, with the gradient enhanced Kriging, this matrix that we have to invert here depends not only on the values, but also on derivatives and second derivatives. Eventually, if you have a large number of parameters, and we like to use the gradients too in our case. So we take the Kriging methods and we put in the gradient values too, and make sure that we do not only interpolate correctly the energies of the surface, but also the slope at the data points we have. Doing this, though, the computational expense increases, and in particular, this matrix goes from being n squared to n times k plus 1 squared. This is something we can live with when we're doing geometry optimizations of molecular structures. If we would like to apply the method to optimizing as a F orbital or any other wave function parameters, that would be a different case. So I'm just going to show you here, for instance, this vector here. When we go over to the enhanced Kriging, gradient enhanced Kriging, we include not only energies, but also gradients, etc. One interesting thing is how to decide these L values. And this is done by optimizing or maximizing something that is called the likelihood. That is the most likely correlation between the surrogate model and a real surface. This is what most people do. They either make a variation and try to find these L values for a particular molecules, or some people do a selected set of L values by doing some validation and minimizing the number of iterations, and then use this consistently afterwards. We will offer a different way in which we dynamically, in a single step, determine these L values without any optimization. The gradient enhanced Kriging also had this property that was lacking in conventional second order procedure, and it is we can compute the variance or the dispersion. We can see how confident we can be on the result that the surrogate model suggests. And we typically look at, in our case, where we have 95% confidence in the energy, or that the energy has this variance. So let me just summarize the Gaussian progress regression properties. First of all, it's an exact interpolator. Any data you have computed before, the surrogate model can represent exactly. And as we add more and more data to the model, the surrogate model will converge to the true function. That is, it can describe anharmonic features. Furthermore, it doesn't need any Hessian update method. As we add data points, we implicitly get that. Further, the method can describe an arbitrary number of stationary points on the surrogate model. And as I pointed out before, it gives you an estimate of the error of the surrogate model. So let me introduce to you how we get away with not optimizing the L value. And the trick is, if you have a single data point, you can select the curvature of the surface at that point by selecting an appropriate L value. And this is a bit like starting an optimization with a guessed Hessian. On the first iteration, you have to use whatever guessed Hessian you have. Afterwards, as you add data points, it's going to compensate and start to produce the real surface. So initially, we compute the L value with this simple expression. And as we add more data points, that's going to correspond in some sense to the Hessian update method on the conventional method. May I ask how much more time I have, please? Somebody?
10 minutes.
10 minutes plus discussion.
Sorry?
10 minutes plus discussion.
Okay. So furthermore, there are these step restrictions. Usually they are geometrical, but we introduce something called a variance restriction. So so with a conventional method, you just have to guess how far you can go. In our case, we're not putting a limit to the actual geometrical distance. We're saying that any displacement is acceptable as long as we can be confident in the accuracy. So in this respect, we do not subject the displacement to a geometrical constraint, but to a variance constraint. So that's why we call it a restricted variance optimization. So let me just briefly show you the flow chart of a conventional calculation. So here we have a restricted step RFO optimization. You start with some coordinates, you compute the gradients, you guess a Hessian. If you have several data points, you can do an update, and then you do a rational function optimization here. You compute your displacements. If the displacements are small, if the gradients are small, you converge. Otherwise, you make a displacement and you continue around like this. With the rational variance optimization combined with a gradient-Snarls Kriging, we have an outer loop structure that looks very much similar to the one I showed you for conventional calculations. So this structure here looks similar, and we call this macro iterations. But down here in the micro iterations, we explore the full surrogate model. So inside here, we use now our surrogate surface and make an optimization, a complete optimization on this surface. The big difference is here, we used to have, in the old method, we used the approximate Hessian. Here, we use the surrogate Hessian. And that's actually an analytical entity, which is trivial to compute. And we micro-iterate here. Once we converged on the surrogate surface, we go back here and we compute a new data point on the real surface at that particular point. There are a few things that we have to select empirically, and one is the trend function, which we have set such that if you're far away from the data points, you're bound. Also, we have to decide how this variance should be changed. So we have an initial value, and then we have a simple equation which associates the norm with the acceptable variance. And as we converge, the gradient norm goes to 0, and we accept a smaller and a smaller variance. So just show you briefly an example on the difference between an H2 optimization with a conventional method and a new method. So here we have, on our right, we have the conventional method, and here on the left, we have the restricted variance optimization. In solid here, you have the true surface, and in blue, you have the surrogate model. Here over, we have also this darker blue area. It displays the variance. So, and in both cases, we now have that we start over at this point, and both of them sort of suggest that the next point should be over here. And as we proceed to map out, now the conventional method wants the next point to be here, whereas here with the restricted variance optimization, we take a much further step. Also note that for the conventional method, the surrogate model now have lost track of these two data points, whereas with the restricted variance optimization, we still correctly represents these data points. And actually now the surrogate model is more or less virtually identical to the true surface. And as we proceed with the optimization, and we now converged with the RVO approach, and a few iterations later, the conventional method converged. At this point, as I said before, the RVO geek, it reproduces the true function. Whereas here, we just at the best have a local correct description of the true function by the surrogate model. So let me present some benchmark calculations. We have taken a set of molecules. One set is called the extended Baker test suite, which contains molecules that are close to the equilibrium structure. We have something called the transition state Baker test suite, which is actually used for transition state optimizations. That is, the structures are close to transition state. But we can actually look at how they converge back to either the reactants or the products. So this is an optimization where we start far away from the equilibrium structure. And then we have the S22 test suite, which is 20 complexes that are held together by weak forces. So here we might anticipate strong unharmonic features. So let me start with the extended Baker test suite. I have highlighted here in this table, we have the 33 molecules. I have highlighted here the only cases where the conventional method outperforms the new approach. And that's also represented here, where the pink is the conventional method and the green is the new method. So on average here, the new method is a significant improvement. For the Baker test suite, I'm doing the same. And the only case we found so far, in this case, where the new procedure performs worse than the conventional method is here for reaction 3, a rather small system. So again, on average, a quite significant improvement. For the S22 benchmark, it's a bit more of a mixed bag. There are some cases where the new method is slower, but not significantly slower, with exception of the complex 14, where we go from 61 to 122 iterations. If we look at this, both this number sticks out as compared to the rest of here, as well as here. And I would attribute this large number of iterations in both cases to that there is an underlying problem with optimization or the selection of internal coordinates. And whether it converges after 61 or 122 iterations is just convergence by luck or random. If we look at a summary now over the benchmarks, we have a conventional method here in these, and we have the green being the new method. Here for the Baker test suite, I can compare with the results by Denzel and Kessner, and apparently both their conventional approach and their approach using Gaussian progress regression performs far worse than the conventional implementation in open mole-cast. For the S22 test suite, I'm showing you the raw numbers, but if we removed this complex 14, again, we would see that there's a clear advantage in using the new approach for optimization. So with that, let me come with a summary. I have today presented a new optimization procedure, a restricted variance optimization. We have been benchmarking this using internal coordinates. That is, we have a potential energy surface or a surrogate model that is rotational and translational invariant. And also we have suggested a way to get away from the hyperparameter optimization and compute that at a single shot step. So to conclude, I think the benchmark calculations have demonstrated that this new approach is on par or better than conventional methods. For the future, we are right now in the group working on using this to optimize transition states and to combine it with constrained molecular structure optimizations, as for instance in reaction paths. But we have also experimented on this, using this method to optimize wave function parameters, in particular SAF orbitals. So let me finish here. Here is a picture of my group. So here is Christian Ritterhoff, is back in Germany now. He's the one that worked on SAF orbital optimizations. And here we have Ignacio and Gerardo that has been working and supporting this project with respect to implementing the core routines and updating the code. So with that, I would like to acknowledge these guys here for funding and you for your attention. Thank you very much.
Thank you very much. And we have a time for 1 or 2 questions.
Actually, I have a question.
Yes.
Hi, thank you for talk. I know that optimization is very important, especially for the big molecules. But my question is, what is the important criteria that we can say we have a good approach to optimize and get the exact state energy of the molecules? Is it RMSD, or is it the minimal energy at the optimization, or both? Because when we have the X-ray structure of the molecules, I know that the structure is close to biological structure, which is the energy is somehow is very good, but when you optimize, then you get minimum and minima and at the energy, but then exact energies are overestimated. So how can we say that we have a good approach exactly?
So if I understand your question is how can we be assured that we're converging to the correct structure on the real surface? And if I go back here to this here, this is just a way for us to position ourselves before we go back and explore the exact model. That model, of course, if it's a Kappa cluster or a COSP2 or a DFT, has its own error as compared to reality. But that's not an issue for the optimization method. It provides you with a stationary point on the parent model.
Right. Okay, thank you.
You're welcome.
Okay, if there are no more questions, then let's thank the speaker again. Thank you very much. And